And I'll share my screen. So I've got the notes up there. Okay, can you see the notes?
Still loading.
Good morning.
Morning, team. How are you?
How you going?
Yeah, we
Good.
can see it.
The notes are there?
Yep.
Right, okay. All right, well, let's get started. So today we're talking about fan types, applications and selection criteria. Again, it's not in depth, but it's to give you an appreciation of the fans that are used most commonly in HVAC. You probably have seen a lot of them, but some of them you may not have, and just to make you aware. Jason Dodd is joining us, but I'm not sure what's happening there. So let's get going. Fans are vital components of all HVAC systems. There are many different types and sizes to suit all of the processes involved. Some of the functions served by fans include outside air supply, toilet exhaust, smoke exhaust, etc., etc. They're also in all the air conditioning units to blow the air around the air conditioned spaces. So in air handling units, fan coil units, DX condensers, cooling towers, air-cooled chillers, and the list just goes on and on. And there are various types of fans are used for the different applications. The list is massive, so a thorough understanding of the application and selection of fans is a fundamental part of what we do. We need to understand how to select fans and what type of fans and how they work. So before a fan can be selected, it's necessary to calculate the requirement at the calculated static pressure imposed by the associated system. Now, this is quite often one of the first things that you'll learn how to do. So we're getting back to the basics here. The calculation of the fan static requires analysis of all the components in the system. For example, in a ducted air conditioning system, the following components might be included: louvers, grills, dampers, VAV boxes, filters, ductwork, duct fittings, attenuators, and there could be other things. You might have coils in ductwork. Sometimes the duct heaters, fire dampers, even hot water heaters are in ductwork sometimes. Static pressure drop is then determined for each component and added together to calculate the total static pressure against which the fan must operate. Just be careful when I say total static pressure. There is total pressure and there is static pressure. Total pressure is the sum of static and velocity pressure. It's static pressure that we're interested in to select the fans, and you'll see all the fan ratings are in static pressure. The ERA Technical Handbook and Design Guide DA13 provide technical information on how to determine the individual component static pressure drops for the ductwork components. And pressure drops for other equipment components can be obtained from manufacturers' literature. So you'll find that all of these things, louvers, grills, VAV boxes, filters, manufacturers' literature is available to help you work out those pressure drops. Attenuators is something we're going to talk about a bit more later on, and louvers as well. So I'll give you some clues on those. We'll just show you the ERA Technical Handbook. This is the 5th edition. There is a later edition out, which I don't have a copy of at the moment, but this one has got everything you need. So air distribution systems, if you look through this chapter, this tells you everything you need to know about sizing ductwork, duct system pressure losses, velocity pressures. There's pressure loss chart for circular duct, circular equivalent of rectangular ducts. This is often handy to get the equivalent circular size of a rectangular duct. And then it goes into losses for various fittings that we use: bends, T's, and so on. Y pieces, T's again, transitions. Just a picture here of DA13. Once again, the area of design application guides tell you everything you need to know. So if you're stuck on something and you need a reference, you'll find it in these guides. And I've just highlighted that reference there. Also, the ASHRAE guides have all this information, but ERA is an application and you need. Fan types. There are many different types of fans available, providing a huge range in airflows and static pressure, as well as a big range in cost. So obviously, cost is an important factor in everything we do. So you need to be aware of that. Some of the commonly used fans in HVAC include wall, window, and ceiling mounted fans, duct mounted inline centrifugal, axial and mixed flow fans, roof mounted inline centrifugal, axial and mixed flow fans with roof cowls, plug fans, floor or cabinet mounted single width and double width centrifugal fans, and so on. Also under slab mounted ILC and mixed flow jet fans used in car park ventilation systems. We'll have a look at those a bit later. Starting with axial fans, they're available as fixed pitch or adjustable pitch type. Adjustable pitch axial fans enable the fan blades to be adjusted to vary the performance if it's found necessary during commissioning. So if you install a fan and find that you're not getting enough air, with an adjustable pitch fan within certain limits, you can adjust the fan blade angle and change the capacity. I'll show you that on the fan curve in a minute. They're normally direct driven, but are also available as belt driven, where there is a requirement to have the motor out of the airstream. Bifurcated models are also available, in which the motor is totally for protection and safety from hazard. I'll just show you courtesy of our friends at Fantech. This is I haven't breached any copyright restrictions, but I'm sure they'll be happy for me to talk about their fans. They've got excellent resources available, so this is why we tend to go to them, because it's easily found and easy to use. So the top one there is an adjustable pitch axial fan direct drive. Okay, so these blades, as I said, they can be adjusted in pitch to change the performance. The next one is a belt-driven fan. It's basically the same fan, adjustable pitch axial, but the motor is out of the airstream. You don't see them very often, but they do have applications. And then bifurcated, which is where you have corrosive or nasty gases in the airstream, and you don't want the motor to come into contact with that. They're totally sealed. The motor is actually behind the hub of the fan, but the whole drive assembly is sealed so that it's not affected by the gas. Huge range of airflows for the different sizes, coming from very low for a small fan down to 300 litres a second, perhaps. And for a very big fan, 2 metres diameter, you can get 70,000 litres a second from those. Fan blade material options are GRP, which is glass reinforced plastic, aluminium, nylon and anti-static for those situations where you've got gases which may be explosive, or most of the applications are GRP blades, but aluminium blades are required for applications like car park exhaust, kitchen exhaust and smoke exhaust. Must be metal. Fan motors, single or three-phase squirrel cage induction motors. Motor speeds range from 2 pole right through to 10 pole. Now I've put in here the equivalent RPM of those poles, and that's something that you'll use again and again. So it's good to get to know what these are. 2-pole is 2880, 4-pole 1440. 4-pole is probably the most commonly used speed for fans. 6-pole, 8-pole, and some of the big ones you can even have 10-pole, which is very low speed. Now range and size from 300 millimeters up to about 2 meters diameter. Airflows range up to 100,000 litres a second if you want to. That's a very big air quantity, but you can get that with a big axial fan. And statics up to about 1,500, depending on the airflow size and speed. So we'll move on to inline centrifugal and mixed flow fans. What I might do, I'll just delete that. Okay. Okay, there's a large variety of these types of fans available, from tubular style to box style. The mixed fan blades are a hybrid between mixed flow blades are a hybrid between axial and centrifugal and can provide greater performance and potentially higher efficiency, but obviously at a cost. So as you're improving efficiency and performance, it usually comes at a bit of a cost. So you've got to weigh that up, whether that's worthwhile. The box style fans can provide some economic benefits in installation that are generally more expensive than axial fans. So you'll find that you're usually comparing a box style inline centrifugal with an axial fan. And I'll just show you some pictures. So this is a small inline centrifugal fan. It's a centrifugal impeller. Installed directly in the ductwork. You can see a little picture of it here with the circular connections each side. You can use fast clamps. So you connect the duct to the fast clamps and to the fan. Gives a bit of vibration isolation and supports the fan. And here's the fan curves. Shows a range of airflows from maybe 30 litres a second up to 400. That's one option. Here's another one which is commonly used. This fan comes in various sizes. This is a mixed flow blade, impeller blade. Again, you've got fast clamps for installation, and there's a variety of sizes available there to give you different airflows. Easy to install, quite reliable. You can get speed controllers, which are generally these fans are all single phase, so you can get a speed controller to adjust the airflow at commissioning. Well, while I'm doing that, I'll go to the so this is what I'm calling a box type centrifugal fan. It's got an inline centrifugal. Yep.
I don't think your image is updating, so we can't see what you're actually looking at.
Oh, okay. So what's up on the screen at the moment?
Just the document that you sent us.
The notes.
Yeah, the notes. Yeah.
Oh, okay. Well, we'll go back to where I started. I'll let this see if this comes onto the screen. Maybe I've got too much stuff here. Is it a picture of the fan coming out?
No.
Oh, there it is.
Yeah. Actually, we have something up. The Powerline series.
Oh, Powerline. Okay. Well, it's a bit out of sync. Oh, well, okay. I'll go to that. Powerline. So right. So this is the charging, is it?
I think it's your internet connection is just lagging out a bit.
Oh, okay.
What if you can send us the pictures in an email after? We could take a look as well.
Yeah, okay.
Yeah.
Oh, that's a shame, because it was sort of good to talk about these as we go through, rather than just listen to me go on. What's up on the screen at the moment?
For me, it's still the Powerline series, the direct drive IoT.
Have you other guys got the
Yep, same.
Powerline series as well? Okay, we'll just have a chat about that while it's there. So it's in a square box. It's an inline centrifugal impeller. So it's relatively easy to install this in ductwork because it's already comes with the flanges on it to suit the ductwork. Compared to an axial fan, which requires squared around transitions and spring mountings and so on, these are a bit easier to install. They have a bit of a limitation in how much air they can deliver. They can go up to, well, as you can see there, 3,000 or 4,000 litres a second. So they have a limitation there. And they're more expensive than axial fans, but sometimes it's worthwhile comparing them. If it's a 3-phase motor, you can control it with a variable frequency drive, which is shown here. So they're quite useful fans. All right, I'm going to jump back to the notes. So I hope I don't mess this up again. So have the notes popped up?
No, but we can see our notes. So.
Okay. All right. Well, if you can see your notes, keep working on that. So fan motor options for the inline centrifugal and mixed flow fans include single or 3-phase squirrel cage induction motors, external rotor motors, and EC, electronically commutated motors. Now, these have some advantages in that they provide improved efficiency with integral speed control. The sizes of the ILC and MF fans range from 100 millimetres up to about 630 millimetres diameter. Airflow ranges up to around 5,000 litres a second with pressures up to about 600 pascals. Okay, well, what's on the screen now, John?
Oh yeah, your notes. It's up to date. Yeah.
All right. Centrifugal fans. So they're available as single inlet, single width fans or double inlet, double width type fans. They're also available with either forward curved fan blades or backward curved fan blades. Forward curved fans are commonly used for lower airflows, such as in fan core units, where the backward curved fan blades are for higher duties like air handling units and large ventilation systems. I'll try and put up a picture of a centrifugal fan. Where are we? Oh, I haven't trouble with that. Sorry, guys. I'll try and open this again. Has that centrifugal fan sheet come up?
Maybe in a couple of seconds.
Okay. We'll give it 5 seconds, and if it doesn't come up, don't worry about it. I'll go back to the notes.
Yeah, it's up.
Right. So some time ago, it's not so common these days. Let's say go back 10 to 20 years ago, these fans were very common. But since then, plug fans, the inline centrifugal fans, mixed flow fans have become more the vogue in what we do. But these fans are still relevant for larger systems. The single inlet fan, single inlet means it's only got the one inlet and one discharge. The inlet is usually ducted, only has one impeller. That's why it's called single width, single inlet. These are generally for large exhaust systems, like for car park exhaust, perhaps, fume exhaust, even large toilet exhaust systems. You might use one of these fans because they're ducted in the inlet and the outlet. A double width, double inlet fan means it's got 2 impellers. Now, these 2 fans both have what they call backward curve blades, fan blades. Some of them are flat, some of them are aerofoil, some of them are backward inclined. generally they're just called backward curved. The aerofoil type blades are obviously the most efficient, but the most expensive. The double width fan has a ducted discharge, but the inlets are open in this case. So you probably see these fans in an air handling unit sitting in the discharge chamber of an air handling unit, where the inlet is open, so the air passes through the coils into the fan and then is ducted out of the air handling unit. They were used almost exclusively up till, let's say, 10 years ago. They're still used, but quite often you will see plug fans used now in air handling units. I'm going back to the notes. Forward curve fans are commonly used for lower flows, such as in fan coil units, whereas the backward curve fans are for higher duties, such as air handling units and large ventilation systems for the single. Backward curve fans are commonly floor mounted on base frames and belt driven. These fans are generally used for high flow and high pressure performance. Forward curve fans are normally installed inside a cabinet, can be direct drive or belt driven. It's common practice to use EC motors in fan coil units for higher efficiency and controllability. Now I'll see if I can move a plug fan. Somehow I've got out of sequence here. Right, so this is, now how are we going? Is that forward curve fan come up?
Not yet. Yep.
Right, so this is a forward curve fan where the blades actually are curved forward. When the fan is rotating, the air is being captured and pushed forward. Whereas a backward curved, I don't know whether you can see my hand signals, but it's more inclined backward and the air is thrown out in a centrifugal fashion. This one shows an EC motor. I'll try and bring up another picture which shows some forward curve fans installed inside fan coil units. You got that one?
Not yet.
Maybe I'll better start closing some of these down.
Oh yeah.
I've got too many. So got it now? I'll close them as I talk about them. So courtesy of Mitsubishi. These are forward curve fans. Obviously 2 fans in this case in the deck, in all these cases. So that shows the discharge side. This is the inlet side. So the return air is coming into the fan coil unit here through the filter plenum. And these are both double inlet. They're not double width, they're double inlet forward curve fans. There's only one fan scroll, which takes up the full width of that scroll, or that enclosure, if you can see what I mean by that. There's dual fans here to get the required airflow, and in this case it's got the motor in the middle. So one motor driving 2 fans, same sort of thing there. I'll close that. Close it. Right, I'll go back to the notes. So fan motors for single inlet and double inlet fans are normally 3-phase squirrel cage induction motors, and the motor speed is normally 4 pole. The speed of the fan is set by fan and motor pulley selections. So when you purchase a fan, you tell them what flow and pressure you need, and the manufacturer will decide what the pulley sizes need to be and the belts to drive. If you have to change the duty of a centrifugal fan, a belt-driven fan, you can change the fan and motor pulleys to get a different ratio, but you may also have to change the motor. If you're trying to get more air out of it, you probably may need to change the motor. Fan motors for forward curve fans can be single phase or 3-phase, or VC motors, as I said. They range in size from about 300 up to 1 metre diameter. That's the fan wheel size, and a huge range of airflows up to around 100,000 litres a second. Just bear with me for a moment. Okay, I'll keep going. Now, there's also high pressure blowers. We don't, in HVAC, you don't use them very often, but you may get involved in some industrial ventilation where you need high pressure and relatively low airflow rates. So these are quite common in mining applications, dust extraction, fume extraction, where you have high pressure. I haven't got the picture of those. I won't try and fiddle with that, but that's something you might come across. Fume exhaust fans. We quite often have a requirement for fume exhaust fans for processes such as welding and laboratory fume cupboards. Which has fume exhaust. This sort of fans are. I'll just show you a picture of those in a second. Fume exhaust fan, single inlet, single width, centrifugal type with the motor outside the airstream. So let's just find that one. Right. So I've got there, courtesy of Needleman, a picture of a fume exhaust fan. Can you see that?
Not yet.
Sorry, guys, but it's worth hanging. You got it?
Not yet. Sorry.
Okay. So give it a couple of seconds. The image I've got here is a Needleman fan, which is a typical fume exhaust for welding, soldering. There's lots of applications for these fans. And it's a centrifugal fan with the motor outside the airstream. Has that come up yet?
Yeah, just came up.
Okay. So Needleman are very helpful. If you've got a fume or dust job, there's limited information available. Needleman are very helpful people to deal with. They've got a full range. You can look on the web and have a look at their catalogue. There's all sorts of applications through car service facilities, special ventilation systems where you can connect hoses to the exhaust while they're working on the cars. All sorts of applications. So they're good people to deal with. I'll close that. The next image coming up is some plastic fans, typically fume-covered exhaust fans. Because the exhaust fumes in a fume cupboard can be corrosive, it's common to use plastic fans. They can be PVC or other plastic material. The fan, can you see that, Dylan?
Not yet.
Okay. The motor is out of the airstream.
Yeah, it's up.
Okay, you got it now?
Yeah.
Right. Okay, so you can see the plastic fans there. So that's commonly used for fume covered exhaust. Close that, go back to the notes. Okay, now I'm going to talk about fan selection. When the application and required fan for performance has been determined, the most appropriate fan for the application can be selected with reference to manufacturer's fan performance details or fan selection software. A couple of the manufacturers, or at least a couple of them, Fantech being one, have very, very good software available. Give me a shake of the head. I know the MEPEC guys have used this. Stephen, have you used the Fantech selection?
Yeah.
Okay. So it's very helpful, and it gives you the option these days of you can change the duty of the fan. You can select the fan, change the duty, and see what happens to it. That's quite useful. Once you've got all those selections coming up, you choose the most appropriate based on criteria such as fan type, example duct mounted, and size. How much space have you got available to install the fan? Do you need, should it be an axial fan? Should it be a centrifugal fan? Depending on the airflow, pressure, you'll get various options. Axial fans are obviously more compact and cheaper than a centrifugal fan, but you might sort of weigh up between an axial fan and a box type inline centrifugal or a tube centrifugal. You look at the NCC compliance, looking for the efficiency. There's a trade-off between fan efficiency and cost, but you want it to comply with the NCC. You look at the sound level, which is always important. The motor details, etc., and obviously the cost. So acoustics, noise generation is always an important factor to consider when selecting fans. Increasing the fan speed will generally provide greater airflow and static pressure, but will also generate a higher noise level. So that's a given. Unfortunately, you speed up a fan, it gets noisier. Always check the fan noise when selecting fans to ensure that unacceptable noise levels will not occur in the building. Acoustics is another topic that we haven't covered. It's a big topic. Probably later down the track we'll go into that in more detail. But it's something to keep in mind all the time when you're dealing with equipment, particularly fans. As a general rule, axial fans are probably noisier than inline centrifugal fans. So that might be a consideration in your selection to get the noise level. We had a look at, I'll come to that in a minute. Yeah, fan curves. I've also mentioned here, it's necessary to select the most appropriate anti-vibration mountings to minimise vibration from the fan entering the ductwork. Vibration is a common cause of noise generation in buildings. So you'll come across this again and again, that if you haven't got satisfactory vibration isolation, you will create a noise problem. And sometimes it can be very hard to find where that noise is coming from. So pay attention to the correct anti-vibration mounts when you're selecting the fans. Fan curves are produced for all of the different fan types to show their performance at varying airflows and static pressure. Now, I presume you've all looked at fan curves, but I'll come to that in a second. The fan curves indicate the allowable range of performance for the selected fan. It's recommended to select a fan at a central point on the sloping section of the curve. This point will provide stable operation of the fan with some flexibility to move up or down the curve if you want to change the flow or the pressure. If your static calculations are not quite right, if you've selected the fan at the right spot, a bit of extra pressure can be accommodated. If the fan is selected at the very high point of the curve, the fan will be in an unstable region and may stall. So I did a quick selection on the FanTech program, and for 500 litres a second at 150 pascals, it gave me a range of selections, as you can appreciate. But I just picked an axial fan to have a look at. So this one, it's good to have a nice steep curve. What that means, if you haven't got your static quite right, if you're too low or too high, you've still got a bit of room to move on that curve. These numbers here with degrees, they're the pitch angles of the fan. So you can vary the pitch angle to get more airflow if you need to. But you can see here that the curves are running out, and you don't want to be too close to that point. You want to be below that. So I've just sort of highlighted around here. This is a good point to select a fan on a steep section of the curve and well away from the highest point. And the output gives you all the data you need: the fan size, the speed, the absorbed power, motor size, efficiency, and then it gives you noise data as well. So the noise data from 63 to 8,000 hertz, they're sound power levels. The column at the end here, dBA, that's the sound pressure level. But quite often, you look at the sound pressure level and say, oh, that sounds okay. But really, to do a proper acoustic analysis, you need to look at the sound power levels. That's a discussion for another time. It's quite detailed discussion, but to do a proper acoustic analysis, you need to start with the sound power levels and work through. Now, Fantech do have an acoustic analysis program. I don't know whether you've used it, but if you work through that, put in the fan data, all the duct work, it'll go right through those calculations, and if you need an attenuator, it'll tell you what attenuator you need. So that's quite helpful. Okay, go back to the notes. It's important to study the fan curve before finalising a fan selection to ensure that the fan will provide stable and efficient operation at the duty point. If the duty point's not satisfactory, just select another fan and start again. Fan laws. I wanted to mention this to you. They can be used to predict the change in fan performance if a single characteristic is changed. So, for example, if you're during commissioning, if a fan is found to be performing below the design airflow, one option could be to increase the fan speed, which will increase the airflow. So if you're using an axial fan, you've got the option to adjust the pitch of the blades. These days, most fans are driven by VSDs, so it's easier to increase the speed. To adjust the pitch on a fan means that you've got to remove the fan and carefully adjust every blade to the new pitch and then put it back in again. That's a fairly time-consuming process, whereas with a VSD, you can speed it up. However, you've got to be aware of a few things. The airflow will increase in direct proportion to the fan speed increase. So speeding it up, you get more air. The static pressure developed will increase in proportion to the square of the fan speed. So speeding it up, your static pressure is going up exponentially to the square. The power absorbed by the motor will increase in proportion to the cube of the fan speed. So let me see. Right. I'll bring up another picture here. Jelen, can you tell me when that comes up? This is fan laws.
Your internet connection seems to be good at the moment, so everything's up to date.
So you got that one?
Yeah.
Okay. So this is in the ERA handbook as well, and I suggest you have a look at this. I mean, these days with VSDs, things are a bit easier to do, but it's good to be aware of this because changing the fan speed has other ramifications. And if you speed a fan up and you work out that you can get the air quantity you need with the fan you've got by speeding it up, the pressure goes up, the power requirement goes up, and what can often happen is you'll need to change the motor. Now, if you've got an axial fan or other types of fans, direct-driven fans, the motor may not fit in the casing. So just be careful. It can be done, but it's not a simple matter of doing it. Just be aware of other things, and also be aware that speeding it up will increase the noise level. As I said while I was looking at the slide, you might have to change the motor. You also may have to change the wiring if you speed a fan up, because suddenly you've got power to the cube of the change in speed. If it's a belt-driven fan, such as a centrifugal fan, and this is where centrifugal fans are great if you want to make these changes, changing the pulleys and belts is necessary, but it's relatively easy to do. So if you go to an existing job, for instance, and you might have a single width centrifugal fan doing toilet exhaust, and they're making some changes to the building, and you need to change the airflow of the exhaust system, so you need to increase it. Then you can change the pulleys and belts on the centrifugal fan, upgrade the motor if necessary, and it's relatively easy to do. But don't forget the noise. I'll keep mentioning that because it's important. Okay, comparative fan costs. For the majority of applications, the most commonly used fans are inline centrifugal, mixed flow for small applications, axial fans for a wide range of applications, forward curve centrifugal, and plug fans. Now, we haven't actually had a look at a plug fan, have we? So if we're getting good reception at the moment, I might bring that up. Are we still going okay, John?
Yep.
Okay, so this is a type of plug fan. These are commonly used in air handling units. So they don't have a ducted discharge. The inlet needs to be ducted, so that would sit up against a wall in an air handling unit and draw the air in. But the discharge from the impeller is into the chamber, the discharge chamber. And the beauty of this is that you can have a discharge in any direction. You can go vertically out of the chamber, you can go sideways, you can go through the bottom, although that doesn't usually work, but it gives you a bit of flexibility. And I've done a really, really rough sketch here of a box. Can you see that?
Yeah.
I've just noted on the top and the side alternatives for discharge locations. And I've found this to be really useful because sometimes you might want the air to come out the side of an air handling unit. And you can do it. I had a job once, it was an existing laboratory. We had to put a new air handler on the roof. And the best way to discharge the air was from the side, because if we'd gone through the top, then obviously you're creating a lot more height. But to come out the side, you kept the height down, and we had to connect to existing ductwork, so it worked out really well. So I will close that. I'll close that one. Now, here's another plug fan. Can you see this one with an EC motor?
Yep.
Okay, so the name plug comes from basically plug and play. These can be bolted onto a wall of an air handling unit, and if they fail, you can take them off and put another one in its place without much delay. So I've got a picture here of some arrays. Well, this particular one's got an EC motor. You can see the fan wheel there. These come in various forms. So here's arrays which are on a large air handling unit. This is quite a common sight these days. These are just different types of inlets. These have got, the ones on the bottom have got EC motors. The ones on the top probably have a different motor, probably not an EC, but so this is the inlet for this one. The inlet for this one is around the edges, those square edges, and then the discharge is out the other side. And the same for this one, the inlet's this side, discharge is that side. So that sits inside an air handling unit, and plug and play, meaning that if one of these fans fails, you can just pull it out and put another one in its place. So that's something you'll come across when you're dealing with larger, fairly large air handling units. I'll close some of these down, might be helping to speed things up a bit. Back to comparative costs. For airflows between around 350 and 5,000, depending on the application, it's worth comparing. If you're selecting an axial fan, compare it with the box type fan or with inline centrifugal or mixed flow impeller. Generally, axial fans will be cheaper to purchase, but the box fans might have advantages in the cost of installation, as I said before. Axial fans are a bit more expensive to install with the squared around transitions and location of flexible connections and so on. Car park exhaust and smoke exhaust fans will normally be axial fans due to their compact size and relatively low cost. The size and cost are the things that have driven selection of these to axials, generally speaking. But if you've got a very large system, car park exhaust in particular, centrifugal fans might be the way to go. Fans, although good practice applies to all fans. So you need to have a look at the manufacturer's recommendations on how fans should be installed. It's pretty common requirement that the inlet and outlet conditions need to be good. Like inlet in particular, you need to have good straight ductwork coming into it, otherwise the fan performance won't be achieved. You wonder why the fan curve can't be achieved with the fan, because the inlet and outlet conditions don't match the way it's been tested. So always check their details. I've got a slide here of, again, this is from the Fantech catalogue. This is worth even copying and keeping it nearby, because these things happen again and again. You'll see fans installed incorrectly and they don't perform properly. Axial fans in particular, which are probably the most commonly used fans, don't perform because they're not installed correctly. So inlet cones, if you've got a free inlet fan, always use an inlet cone. Without an inlet cone, you're going to affect the performance of the fan. If you've got a bend coming into the fan, don't do the first one. Do something like the second one. Put a radius bend in with vanes, push the fan back and make a long transition into the fan. Flexible connections. You don't have the inlet flexible connection right at the fan impeller, because the negative pressure at that point draws the flexible connection in and creates disturbance at the inlet. So they're showing eddies being caused by this flexible connection. You need to move it back upstream by at least 1 diameter and have a piece of straight duct coming into the fan. Duct restrictions at fan. Don't have a sharp transition at the fan. Have a long one. Preferably do what is done here. Have a straight piece of duct the same size as the fan inlet, and the air can straighten out before it goes into the fan. This is all basic fluid mechanics, really. Pressure recovery. Don't discharge the fan without some sort of outlet ductwork, because that will affect the fan performance as well. And if you've got an obstruction, if you're discharging air outside but close to a wall, move the fan back from the wall. So this one shows a bit of a transition at the outlet, and then at least 1 fan diameter back from the wall. And for inlets, same sort of thing. Put it back 1 metre from the wall and put a cone on the fan to get the best performance. And when you've got an inlet to a fan, always put a mesh, a guard on the inlet, so that people don't get clothes drawn in. If you get too close, you might stick your hand in the fan. It has happened, and on very big installations, fans create huge negative pressure at the inlet. I've been into fan chambers, I'm going back a few years, but it was a centrifugal fan, a big double width, double inlet fan. You have to hang on to something to stop yourself being drawn into the fan. So people around fans, and make sure they've got guards on them so that people can't get injured. That's the end of the notes. I'm sorry about the transmission today. Sometimes we have these problems with the internet. Are there any questions?
I had a question. With the
Yep.
fans, you said that it could be like 2 poles or 4 poles, 6 poles, 8 poles, and that determines the fan speed. Would there be any reason why you wouldn't pick 2 pole, which is 2880 RPM, compared to like a slower speed? Or is there some advantages using slower speeds over higher speeds?
Okay, well, yes, advantages with slower speed is your fan will normally be smaller. That's one. You will sometimes get a better fan curve with a 2-pole fan. There's nothing wrong with a 2-pole fan. The people used to say, "Oh, I don't use 2-pole because they because they're traveling at a higher speed, they're not going to last as long." That's not true. Okay, so they're going to have the same life. I guess the only disadvantage with 2-pole is noise. You'll find for the same duty, a 4-pole fan will be quieter, but obviously and a 4-pole fan, because people cost more, so it'll be more expensive. So I have issues using 2-pole fans, 2-polers, but just beware of noise. That'll be one thing. You will normally get good performance and a smaller fan, which is great, and less cost. And the same, we'll talk about pumps later on, and the same pumps, 2-pole motors on pumps are okay and quite often recommended because it's more economical, it's smaller, you get quite often get a better selection with a 2-pole than a 4-pole. But as the speed reduces, the noise comes down, but the fan gets bigger. So that's the trade-off.
Mm-hmm. Yeah, thanks.
Okay. Anyone else? Okay. No other questions?
No.
Well, once again, sorry for the interruptions in the transmission, but I hope that was of some benefit to you. You've got the notes anyway.
That's great. Thanks.
I've shown you a lot of fan sheets. Sorry.
Thank you.
Oh, you're welcome. Sorry, I can't see you. Is that Jason, is it?
Yeah, it's Jason here.
Yeah, sorry, mate. I can't see your picture there, but yeah, I can see your name is there.
How are you going?
All right, no worries. I was just going to say, to finish off, have a look at the Fantech catalogue. There's a huge amount of information in there, and it should become. Oh, I can see you now, Jason. Where are you going again?
Yep.
Huge amount of information. Just have a flick through it, see what's there. It's online. All this stuff's online, as you know. It's very helpful when you're looking at fans. So you need to get to know fans pretty well. They'll become your friends. All right, guys, if there's no other questions, I'll let you go and see you next time.
Okay, thanks.
Thanks.
Yeah.
Thanks, mate.
Later.
Thank you.
Bye.
Great. Bye.
See you later. You just